Our next speaker is Yupeng from Uber. Topic is about disaster failover in multi-region Kafka at Uber, which is actually a pretty common theme in deployment and provisioning of Kafka clusters, right? Because when you start your first Kafka journey, you may start with a single Kafka cluster sitting in a single data center, and all of your clients are likely to co-locate it with that cluster as well. But as you scale your business logic, you will soon realize that you will need multiple clusters or a single cluster spanning over multiple data centers. Soon you will realize a lot of those questions come up from your setup, like, do you want an active manner, or do you want an active standby manner? Or do you want to actually tolerate like controlled failovers from one data center to another? Or you want to also, have handled unexpected failovers as well? So Yupeng today is actually going to talk about all of those, best practice experience from Uber. And with that, let's welcome Yupeng.
Thank you, Guozhang. All right, good evening. Thanks for having me. And also thanks to Confluent for hosting this meetup. Glad to see so many people here. Today I'm going to talk about some of our best practice we learned at Uber. I'm going to talk about how we do the disaster recovery. We just learned how important that is. You have one mic off, then we can fail over to the other. I'm Yupeng. I'm the tech lead of the streaming data team at Uber. Our team owns Kafka and also the ecosystem, the pretty complex ecosystem we built on top of Kafka. And today, Uber is like a global business, and we run a lot of data centers across the globe. I will talk about how we solve this problem at Kafka layer. A bit about myself. I'm an engineer at Uber, part of the streaming data team. Previously, I worked at Luxio, an open source distributed storage system. I'm a PMC member there. And also I work at Palantir across the street, working on big data like Spark, Hadoop stack. I also did my PhD at UCSD on database, so I've been in this data system domain for quite some time. Let's talk about how the data infrastructure at Uber. Over the years, Uber first started using Kafka more than 5 years ago. We had a handful of engineers, and along the years, we have built pretty complex system internally, and we had a pretty large team maintaining Kafka. And also, we saw that Kafka is so important, it actually became a cornerstone of the Uber tech stack. So from a 10,000 feet high-level view, Uber actually, you build the entire technology. It can divide into two parts. One is an online application world that we have Uber apps, you have riders, drivers. There's a stream of different events, and we do matching and stream join, those kind of operations. And on the other hand, we have an offline world where we do a lot of data analytics operation. So ops, data scientists trying to derive insights from massive amount of data that we collect. And Kafka is actually glue of all the components internally for different components. And if you look at this diagram here, you can see the producer, the upstreams are different applications that we have. Your mobile app, your Uber app, or Uber Eats, or Uber Free, those kind of drivers, and requests coming in flow into Kafka. And on the other hand, we also have a lot of ongoing transactions in our database, internally with, for example, Cassandra or MySQL, many other database systems. So many transactions going on, generate a lot of logs stream into Kafka as well. There are definitely more upstream applications. If you look at downstream, how we can leverage or use these events. So we have different kind of processing of this data. So for money related, how we do payments, how we do accounting, and how we do pricing. Actually, in this talk, I'm going to talk a bit about how we do pricing over Kafka. And we do log analysis via ELK. And importantly, stream processing, also a really big topic and really important component internally. Today, we use Samza and the Flink for building any real-time analytic dashboards. So operations across the globe can see how many driver or trips ongoing in every city, like every country, and even like in the in each continent. So the executive teams and operations can have a good understanding of how we business is running and operating, like at a minute level. And move on, we can to see there's like a Hadoop world. We use like entire Hadoop stack. We also use like Spark and Presto, the analytical like query engines to do pretty advanced and sophisticated analysis on the data that we have. And we also do like data backup. So we will write like Kafka into like S3 or Hadoop, and so that we can do backfill when anything wrong happens. So just put like a few categories on our use cases. The reason I put these categories is actually, if you look at each of these, they represent a pretty unique use case of Kafka at Uber. And they have different kind of requirements for the Kafka itself, and also for the components we build on top of Kafka. So some of them like pops up systems where you can think of our applications will like do some like async RPC and pass information to the downstream. And some of them, let's say, hey, I just like fire and forget. I don't care about like the data loss or something. But some of them really care about those. And some of those applications like database changelog, because they are like database transactions, they care about ordering like very seriously. But for any applications, actually they don't care about. It's not like a requirement. And ingestion into data lake is also like important because there are so large volume of data. So each day we run complex jobs to make sure data can flow in our data lakes across different regions and globally. And lastly, like for logging and metrics gathering, also they generate such a large volume of data. So we actually have dedicated clusters for this kind of users. So if we look at these use cases, you can see the importance of per use case is different, and we have different tiers of our services and users and provide different SLA guarantee to them. So one side to summarize the scale of Kafka service at Uber, we have trillions of messages per day, and petabytes of data is such a large volume that actually we have one of the largest like deployments of Kafka clusters over the globe. And we have quite a lot like internal users and services using us. And you can see along the years, we actually benefit a lot from Kafka community because we run such a large scale Kafka deployment internally. We actually hit a lot of like performance bottleneck that is not necessarily exposed by smaller deployments. So we submit a lot of like Jira requests and bug reports to the community. And we are very thankful that the community can actually help us address many of our problems. And in return, we would like to do the showcase and sharing of our learnings and practices in this kind of like volume. So let's talk about like multi-region and Uber. This actually is a company level strategy that generates requirements to our entire technology stack. So the key points that like provide business resilience and continuity is our top priority. That means if there are like outages or natural disasters like earthquake or something strike us, we have to survive those outages, and our business shouldn't have any like major impact. And the other motivation is that we want to provide reason isolation to avoid cascade failure. So this is, I talk about like the natural disaster, and those are like on the hardware side. So the second point is more from software side, like bad configurations, bad deployments, like may spam across different deployments and tear down our running like applications. So one example we like to use is think of like the classic thing of Titanic. Even though Titanic have so many compartments, they're actually now still at the top. So once the water fills in, if you like pollute compartment by compartment, and eventually will sink the entire ship. So we take this learning and we do the practice that we want to make sure certain isolation among different deployments in different regions. So if there's something we deploy, we actually want to wait for some time to see and observe how it's going. And once we have the green light, we will do the rolling like deployment in other regions to make sure our business will not fail entirely by something bad code change. And we want to take good care of customer experiences. So importantly, some of our applications really require low latency. And as our business scale, we actually serve traffic across the globe. How I make sure we can handle each user request in a closer region, in a loader manner is actually quite important for some of our use cases. However, there's also multi-region generates challenges, which is about data integrity and consistency. Because some of our applications, they do care about consistency. For example, you don't want to be billed twice, or drivers, like, they want to be paid, right? But from company perspective, we shouldn't like pay twice, right, for the driver. Data integrity problem is that, like, think of like you have your failover from one region to the other, but you want to make sure all the requests you have handled shouldn't be duplicated. Like, for example, user like Uber apps, you shouldn't be matched twice with different drivers. So data integrity consistency is also like a very important requirement for us to take care of. Oops, sorry, I have some typo here, but the last one I was meant to talk about, like compliance and like security we talked about. And flexibility. I have some typo here. So regarding compliance, there are like certain requirements from different countries that say the data I generate should stay within this country. So that means for some of our regional service, we have to make sure the data that flow in shouldn't flow out to other places. If you have multiple countries like this, then you will see your data become like destroyed in different like regions. And regarding the flexibility, is that like at Uber, we actually take a hybrid approach, leveraging both on-premise and different cloud vendors. So we can freely move a region deployment from like different like physical infrastructure underneath. And therefore this provides us quite flexibility and also like negotiation leverage from different vendors. So let's see, with the multi-region strategy installed, what we shall do from the technology perspective. Let's say I'm an app builder of this app or rider app, like what we should change or consider for my services. So one thing is like we have to make sure the service is highly available, so that the service should expect like automatically on-demand region failover. It could be like a real disasters, or could be like we do some common practices periodically to fail over our service to make sure everything is implemented and deployed correctly. And we also want to make sure this to be like highly flexible. Like, so we take this approach that we shouldn't put all the basket, so all the eggs in one basket, meaning if some deployment is done, the entire Uber app become unavailable. This is not acceptable. So what we do is that like we divide the deployment into multiple small sub deployments, so that we can freely move one small deployment around, and this one small deployment can take like percentage of the traffic, let's say 1 to 2% of the traffic, and serve those. And they are like isolated. So if you move this deployment from one region to the other, it's fine to the infrastructure per se. And naturally, if you have Uber data, we are sharded by the geolocations because we have a really lot of like local business. So this gives us the leverage that we can divide data and shard them using certain geo information. This actually provides pretty good load balancing strategy for our deployments. And also the trade-offs in SLA. So what I mean by this, so one is that some of the applications, they really need like a local data or like a regional data. So your data is produced within the region and consumed by some other application within the region. It's like a self-consumption. However, some other applications, they require an aggregated view to do some holistic or global analysis. Like for example, our data lakes actually the aggregation of all the data from across the globe. So a data scientist can run some query to do the holistic like analysis. Also, there's the latency and consistency trade-off. There's like famous like CAV theorem, and there's like extension to this theorem that when there's like no partition, you have to choose between latency and consistency. So for us, we actually educate our internal users to make sure they understand what property they really need and these services can rely on and pick the right like Kafka service. And lastly is a very important principle or like learning from us is that like we observe there are a lot of complexity in common to deal with region failover and activities. If all the application layer do this problem independently, they will actually solve the same problem over and over again. So what our strategy is that we try to push this complexity down into the storage layer. So this combined with the strategy about that, we try to make sure application to be as stateless as possible. And if there any stateful information they want to share, they should push it down into the storage layer. So storage could be like database, could be Kafka, so that we can share this information and provide different active type for the applications, and therefore simplify our developers' life. And they don't have to worry about a lot of like disaster recovery problems. And so let's see what this means to Kafka. So we already know what the application developer they want to do. They say, hey, I want to throw this problem to Kafka. You solve this problem for me. Let's see how we can solve that. So let's look at this problem like layer by layer in Kafka. First is like the producer. So one requirement or one constraint we install is that like data should be produced locally. That data should produce within the local region. And we strongly discourage to produce data in the remote region. So there are like latency and there are like throughput issues, and moreover, this may incur a lot of cost if the infrastructure is on the cloud. There's like data transfer cost. So what we try to do is like we make the producer of the application to be like region agnostic as much as possible. So they just say, hey, I want to produce information. And then the default policy will just go to local. And we store this in the regional Kafka cluster. And then we do the data aggregation that we replicate the data to the different like egg clusters. So that egg cluster provides the global view. So keep in mind that here I use an example of 2 regions, but we not necessarily only have 2 regions at Uber. And then we have a active consumer in this case. Active consumer is relatively simpler to the active passive case. So one of the reasons is that like they do not do to track the outside information of the consumer. So each consumer work independently, consume local information, and the community manages their own offsets. So for example, like data ingestion is we are using this double, triple, or O compute depending on number of consumers. So I give you one example of the dynamic pricing that we have. So dynamic pricing is a very important service to Uber. So that gives the balancing tool of our supply and demand. So if you like look at like one local region, if we know they are short of like drivers, we will change the price to attract more drivers to this local region, so that we can to balance these 2 parties. It's quite critical because it generates really to our revenue. How we can do this and what the challenges are. It's interesting to see, even though the dynamic pricing is really a local service, meaning all of your input will from local, like you have local driver, local rider, but we have to use active to do this. The reason is that like our dynamic pricing algorithm is very, very complicated. So we use advanced and sophisticated machine learning technology to calculate the ultimate the price for both parties. So it's a very complex streaming application and use a really large memory footprint. So that we cost like terabytes of memory, like hundreds of machines just to compute this. And think about like if you're so large state, how we can carry over this state to the other region, right? This will be very, very difficult because you have like a streaming like content keep flowing in, and to determine price, we actually have to look back in the history, like for example, the past like 1 hour, 6 hour, 24-hour window to determine how we should like the system should be to behave to provide this pricing. So when the disaster happens, we lose the state of this computation, and to regenerate or to rebootstrap this computation state actually takes pretty long time, and therefore we cannot satisfy the latency requirement. And lastly, this is really like a time-sensitive application. So because it's a dynamic like pricing calculation, right? So your message can arrive late, but if you arrive late, then the algorithm will not count you in. So consistency is actually less important. It's okay to lose like 7% of this traffic, but calculating a timely and effective price is a top priority for this. The way we do it is that, like you can see on the left-hand side, we have demand supply coming in, landing in the regional Kafka, and then we aggregate to the every Kafka clusters. And in both regions, we do this double compute. We calculate the same pricing, and we try to store these end results in a Kiwi store. And you see there's like a one active service, like telling you that given one like region or one location of this app, which data center or which region is primary, so that to avoid it's a double commit problem. So here, let's say I'm in San Francisco, then probably like the West Coast is the best like region to store this information, so that the backup region will just discard this result. So, and then the end consumer will also query this Kiwi store. So keep in mind here, the Kiwi store here must be all active as well. So as I said, like we try to push this active complexity to different components. So Kafka, Kiwi store, database, they need to be active. So when the disaster happens, we just fill entire like the region to another, and the all active like survey we just flip and say, hey, you are the primary, now you can commit. So one key component in this diagram I showed is in the data replication. How can we efficiently and reliably replicate data from one cluster to another? Due to time constraint, I couldn't go through the details of this, but we have open sourced this technology as you call Replicator. It's built on top of the mirror maker tool that provided by Confluent. And we did certain optimization on top of that. For example, like we made it really easy to use and operate. You can dynamically to add and remove topics, add whitelists, and also we changed the high-level consumer using the mirror maker to low level, so that we have finer control of the like replication behavior, and therefore when there's topic added, you will not see like rebalancing, which may cause some performance problems. So if you're interested, please like check out this blog and our GitHub. Okay, so let's see the last one. So how I can do the active and passive consumers, which is very challenging for us. The reason is that like whenever you have application or consumer failover, we have to remember your upsides or your progress, so that can carry over your state to another region to continue your processing. And active passive consumers actually heavily used by some consistency heavy applications. For example, our internal accounting applications, they really want to make sure all of the writes coming from one region to ensure the data integrity. So let's look at this offsite challenge, thing challenge. One, we have several requirements. One is that several important use cases cannot tolerate any data loss, so we cannot resume from the latest offsets. And also we want to minimize the number of duplicates because we have a pretty long retention date. Reprocessing every message will be too much like compute resource based. So we cannot consume from the smallest one either. Some of other offset sync to our approach use a timestamp, but that's become but we have some constraint that we actually, our messages do not have a header and timestamp because we're some cluster using like a lower version of a Kafka cluster. There was no header information. And also, even for the messages that we implement schema, those kind of schema information to interpret that and get timestamp actually be very expensive. And lastly, we have like this out of order problem. So recall that we do the data replication from regional to egg. And if they are in different regions, this data replication is kind of like a merge. But because of location difference, they will actually take different time to land. So think about this, like for the from region one, if you copy from to region one egg, it will be arrive faster than the 2122 copy here. Similarly for this case, then you will see this mismatch ordering in the messages in the two egg clusters. And our active passive consumers are reading these two egg clusters. How can we ensure we do not have data loss and how we can minimize duplicates? So that's how we build our internal offset management service. One is that we have to checkpoint the offsets. And we do this by Replicator that periodically will report offsets from the source to the destination. So think about like you have a replication flow from source to destination. Every few, for example, seconds, we can store checkpoint the state, like what's the mapping from the source offset to the destination. And the offset manager manage the information and store this information in the database and can do the translation job. So a client may ask, say, hey, this is my offsite at the source cluster. Tell me what's the translated one at destination. So by providing this API, there will be like a job periodically translate these offsites for different kind of topics and consumer groups. And lastly, we'll try to like push this offsite and written down into the destination cluster so that when the consumer failover, it doesn't have to look up offsets, but for our internal consumers, our client libraries, they have ability to look up the offsets. So I'll give you like a one flow to see. So all the offsets are like zero indexed. So you can see from region one to egg one, we record this offset checkpoint like from 1 to 1, so the second message. And similarly, in the region two, we have 2122. And then we do the copy from region two to region one egg. So the mapping become like from 1 to 3. Similarly, we have from like region 1 to egg 2. So we keep doing this kind of practice to record all the information to get a checkpoints table. With the checkpoint table, we can look it up and find the mapped offsets. So assuming we have a consumer that at this index 6 here, and the algorithm is try to find all the source offsets of the most recent checkpoints of all the source clusters. And then we take a mean of this check offsets. The purpose is that like, if we find a mean, then we can guarantee there's no data loss. We have consumed everything. So in this case, I said the two source is of this we have seen from the previous slides is like 2.12. So this actually maps to the file maps to here, the 3 here, based on the previous table. And similarly for 3, this maps to 1. So we take a mean here, which is 1, and then we do the mapping to this egg cluster on the left-hand side, which actually become here. So that means when we do a failover, the client here should read from 1 to start consumption. So there's one interesting corner case which is some optimization. So that's when we have an active passive producer as well, meaning the information will flow to one primary like region, and it can fail over, and when it fail over, it goes to the other region. But when it produces to a local region, the other data center, there's been no traffic in. So why this become a problem in our algorithms? If you look at here, this is the existing state. And we can see if a consumer is on the right-hand side, it's like there's a current position. And given the algorithm, they should go to 3 because this was 2-1 goes to, right? Now with more information and message flowing into the region 1, the upsides from my primary region moves on, but you will see the translate upside in the backup does not move at all because it's bottlenecked by the slowest one, even though in this case, there's no traffic coming in the region 2. So that's how we change our algorithm to deal with this corner case, which is that like once we do the translation, we actually do a check to see if the source offset is the latest one. If it's the latest one, we know we can like safely ignore it because there's no information there, and only take the rest of the source clusters as input. So this basically go with a overview how we deal with this axial passive consumption use case. So we have seen this offsite management tool is very useful, and typically they should be paired with our Replicator tool, because right now with our open source Replicator, there's no passive like active passive failover support, and the existing open source user have to build their own equivalent tool for this. So we do have a plan in the future considering open source our offsite management tool as well. So yeah. That's pretty much my talk. Thank you. Any questions?
Push the button, hold it.
Okay. I noticed in one of your earlier slides, you had the producers, the apps. They go to Kafka, and then they go to consumers. Is there ever a feedback loop from the consumers back into the Kafka store?
You mean by the backfill, or
Like the consumers, I noticed there are a whole slate of consumer. Do they ever feed back data into Kafka, or do they?
I mean, it's for example, it's common practice to see like streaming process jobs. They do some calculation and then they can write data back into Kafka, but not necessarily in the same topic, but in other topics.
Okay, oh, thank
you. So the question I wanted to ask is if you actually had an active failover during surge pricing. But then I guess the better question is in the world of Chaos Monkey, do you do any sort of testing to make sure that you know that all your scenarios will actually fail over properly?
Yeah, that's a great question. We actually do regular practice internally to do this kind of testing to make sure our failover strategy is implemented correctly. Because like a natural disaster kick in maybe like very infrequently, right? But how can I make sure the code we write is in the expected behavior? So we actually do real simulations of this.
But you don't do them live in production.
This
It should work though.
we actually do this as well. Yeah, use a real traffic. Yeah.
So when you have an unexpected failover, do the clients need to manually switch over to the new DC, or it's actually automatic as well?
So it depends on active, or active passive. So for our clients doing the active passive, we actually check with the same like all active service to ask which is a primary data center. So I can reconnect to that data center and our region for consumption. But for the active one, actually, such coordination is not required. So each service or each application just running on by their own, I assume they are the only consumer in the world.
Cool, thanks. No more questions? Okay, let's thank Yupeng again. Thank you.
Thank you, everyone.